Okay, well, good morning. I think that's better. Okay. So when I was writing my textbook on pattern recognition and machine learning, I wanted a chapter on sequential methods, models of sequential data. And the two main models, the Kalman Filter for continuous states and the hidden Markov model for discrete states. And so I decided to look at a couple of books on Kalman filters just to, learn a little bit more about them. And I found a couple of books called sort of Kalman Filters, Introduction to Kalman Filters, and I started reading them. And I found them very heavy going. And I formed the view that the way that the material was being presented was really quite complex and obscure, at least from my point of view. I found it very hard going. And this, to me, seemed a bit of a shame, really, because as far as I can see, the idea is extremely simple. And I've come to the view that if you want to learn hidden Markov models, you want to learn Kalman filters, or many of these other models, the best way is just to learn graphical models in general, learn about the sum product algorithm that we derived yesterday, and then all this other stuff comes for free. Okay? And not only does it all come for free, and this is by far, I think, the easiest way to derive the equations of Kalman filters and hidden Markov models, but I think you get much more insight into what the model is all about. And so I'm going to try to illustrate that sort of point of view by taking you through one of these examples, which is the Kalman filter. And we've got a lot, not all, but we've got most of the sort of machinery that we need to do this from the previous two talks. So let's imagine we want to solve the following problem. Let's imagine we're trying to track somebody's hand. Okay, gesture-based interfaces are very popular these days. So let's imagine we've got some sort of sensor that can detect the position of a hand. Now that might be some computer vision system, that might itself involve probabilistic models and so on. But let's just imagine for this talk that we've got a sensor which can detect the location of the hand. And we'll begin by supposing the hand is stationary. We just want to know what the hand is stationary, we want to know where it is. We've got a sensor and it can detect the position of the hand. But the problem with our sensor, in common with most sensors, is that it's noisy. So if I measure the position of the hand several times, I'll get different measurements. Okay? So the sensor is not directly measuring the true position of the hand, and I want to infer the true position of the hand. So if you imagine that the hand location is one-dimensional for a minute, just a horizontal position. So I've got a bunch of measurements of the hand, and this is corrupted with some sort of random noise process. And so what am I going to do? What would be a sensible thing to do? Well, I guess an obvious thing to do is just to average the data and to treat that as my best guess for the position of the hand. And that's absolutely fine. That's a perfectly sensible thing to do. I'm going to show you a slightly different way of doing it. And at first, this is going to seem a bit more complicated, but actually it'll turn out to be a lot more powerful. Okay? And you'll see why in a minute. So instead of just averaging the data, we're going to get there, but by a slightly more complex route. What we're going to do is to introduce a probability distribution over the position of the sensor measurement. And so we're going to model that data using some sort of distribution. So it'll be some distribution now over a continuous variable. So we need to think about distributions over continuous variables. Well, yesterday we mainly looked at discrete variables. So we now need a model for distributions over continuous variable. And by far the most widely used is the Gaussian distribution. Probably most of you are familiar with this, but let's just review this. So this is a probability distribution over a single continuous variable x, going from minus infinity to plus infinity. It's governed by two parameters, mu, which we call the mean, and sigma, which we call the standard deviation. And sometimes instead of using sigma, we use sigma squared, the square of the standard deviation, that's called the variance. And sometimes it's useful to work with the reciprocal of the variance, we call that the precision. And that's the well-known mathematical formula for the univariate Gaussian distribution. So that's the Gaussian in one dimension. Of course, we can have a Gaussian in many dimensions. So this shows two variables, x1 and x2. And this is a joint Gaussian probability density over those two variables. What these ellipses represent are contours along which the density is constant. So again, this is a sort of a bell-shaped curve, but now its peak is in the middle here, and it's falling off in all directions, and like a sort of hill on a sort of hiker's map, these are the contours of constant density. Okay, so what we're going to do now is build this probabilistic model for the location of the hand. And we're going to use our Gaussian distribution. So x is this noisy measurement that we make. Okay? And it's going to be governed by a Gaussian distribution parameterized by mu, where mu is the mean. Okay? And so mu is going to be our representation of the true but unknown position of the hand. So mu is the true position, but the measurements are noisy measurements that have noise distributed either side of the true value mu, which is unknown. Now, because mu is unknown, we're going to represent it using a probability distribution. And we already have a good probability distribution to use for that, because mu itself can be from minus infinity to plus infinity. It's a real number. And so again, we can represent the distribution of a mu by a Gaussian. Okay, so we now have two Gaussian distributions. This Gaussian distribution, so this factor represents a Gaussian distribution over the variable x. It's conditioned on mu. This represents the noise on the sensor. So the variance of this represents how much noise we have on the sensor, and it's centered about a particular value mu. Mu is the true position of the hand. We don't know mu. Our goal is to find mu. So x is the thing we can measure. Mu is the thing that we want to know. And again, we describe mu by a Gaussian distribution. Okay, so this is the factor graph. So the same factor graph for the murder mystery. So yesterday, this was the culprit of the murder. This was the weapon. And different culprits chose different weapons. We observed the weapon, and we used inference to compute a revised distribution over the culprit. So here, different choices for mu will shift this Gaussian distribution left and right, and then given the value for mu, we then draw x. In this sort of generative view, we draw x from that distribution. So we take mu and we add a bit of noise, plus or minus noise. So that's our factor graph, and that's our probabilistic model. So we talked about the generative view, so that's our model. So the second stage now is to observe some data. So we observe the value of x, and then the third stage is to do some inference and compute the posterior distribution and to see what we've learned about the position of the hand given that noisy measurement. Now, of course, we're not just going to make one measurement, we're going to make several measurements. So this is what the factor graph looks like. So here's the scenario then. Somebody's holding up their hand. Their hand is in a fixed position, but we don't know what that position is. We'll call that position mu. We now make several measurements with the hand in that position. Okay? So there is a single value for mu. We don't know what it is. But for that particular value of mu, we're going to make several measurements. Okay? So each of these is an independent noisy measurement. We've taken the same value of mu and added a bit of Gaussian noise. Everybody happy with this model? I know it's 9 o'clock in the morning, but question, yeah. No, great question. So is the hand moving? Let's be super clear about this. For the moment, the hand is stationary. Okay? This is a fact about the world. The hand is stationary in a particular position. We'll call that position mu, but we don't know what it is. Our goal is to measure where the hand is. So mu is a single precise value, but we don't know what it is. So our state of knowledge of mu is going to be represented by a distribution. That's our uncertainty over where mu is. Okay? That's why there's just one node here for mu, but there are multiple measurements because they're all made with the hand stationary. So I measure where the hand is, then I measure it again, then I measure it again. The hand itself is stationary, but the measurements are jumping about because our sensor is imperfect. It doesn't measure the perfect position of the hand. It sort of adds this noise. Yeah? Everybody happy with this? Okay. Let me introduce a little bit of notation. Okay, so that's the inferential direction that we want to, that's the inference problem we want to solve. So it's useful to introduce a little bit of notation. The graphs like this can get very cluttered. If I had 1,000 measurements, I wouldn't want to write 1,000 nodes out. And so we have a little shorthand notation, and it's called a plate. And there's some obscure historical reason why it's called a plate, and I've forgotten now. I keep trying to remember. It's very bizarre. But anyway, it's called a plate. And all it means is, so a plate is simply a box that encloses part of a graph, directed or undirected graph, or in this case a factor graph, a box that encloses part of a graph. In the corner of the box is a number, and that tells you how many times you replicate the thing that's inside the plate. So if n were 3 here, this graph would be the same as that graph. Okay? So it just means n identical copies of what's inside the plate. That's all it means. Okay? Okay, what happens if we do inference on this graph? Okay. So here's what happens. This is a graph of mu. So mu is the position of the hand. Remember, the hand is stationary. There's a value for mu. I don't know what it is. A true position for the hand, and I'm trying to learn it or to infer it. Before I've made any measurements, I have some broad prior distribution, which is shown by n equals 0. So n here is the number of measurements that I've made. So when n is 0, all I have is my prior distribution. I've not made any measurements about the hand. I'm hopefully, it's somewhere in the field of view, but I don't know where. And so I start with a broad distribution centered on 0, representing my prior beliefs about where the hand might be. Now we make one measurement of the hand position, one noisy measurement, and we run inference to compute the posterior distribution. So that's just applying Bayes' theorem to compute the posterior distribution of mu given this measurement for x. And what happened? What does the posterior distribution look like? Well, two things have happened. So that's represented by the green curve, n equals 1. You see the mean has shifted, okay? Because the value for x on the mu scale would be out here somewhere. So the mean has shifted. So I think now the hand is more likely to be to the right of 0 than to the left of 0. So I've learned something. And if you notice, the variance or the standard deviation of this Gaussian is less than at the start. The Gaussian has become narrower. So the width of this, remember this is the distribution of mu, the unknown position of the hand. The width of this represents my uncertainty over where the hand is. And that's, because that Gaussian is narrowed, I become less uncertain. So if you think about the movie recommender demo, remember when I rated a movie, the movies were all sort of spread out, or they're actually all near the middle because they were very uncertain to start with, and as I rated a movie, they spread out. The probabilities moved towards 0 and 1 in that case because I became less uncertain, or the system became less uncertain about my movie preferences. If we see 2 data points, the mean shifts again and it narrows, and after 10 data points, the mean has shifted again and it's becoming very narrow. So what this means is, as I observe more and more measurements from this noisy sensor, I become less and less uncertain about the position of the hand. Okay? And if I observed an infinite number of data points, this Gaussian would become a delta function. It would have 0 variance. It would collapse down to a spike, and I would be completely certain about where the hand was, and that value would just be the average of the data, which was our sort of heuristic that we started with. So it was a long, complicated way of taking an average. Okay, but it's going to pay off in a minute, I promise. Any questions about that? Okay, now let's make life harder. So coming back to your question, what happens if we have this, we're making noisy measurements of the hand, the hand's moving. Okay, so the hand is sort of moving, and I want to know where the hand is. And 30 times a second, let's say, I can make a measurement, but the measurement itself is noisy. So we're making these noisy measurements 30 times a second, and in real time, I want to know where is the hand? Where is the hand now? So I've been measuring values of this hand location 30 times a second for a while, and now in real time, now I want to know where is the hand. What could we do? Well, one thing we could do is we could just take the most recent measurement. Okay, so the most recent measurement was measured with the hand in its current location, so that's good. It's noisy, that's the downside, but that's the first sort of heuristic. I just throw away all the earlier data, ignore it, and just use the current measurement. So it's a noisy measurement, but it'll give me some rough idea of where the hand is. Can I do better than that? Well, when the hand was stationary, if we just took one measurement, it would be very noisy. We took lots of measurements and averaged them, and we got a much better idea of where the hand was. So combining lots of data together is much better than just using one data point. So can we use this other data that we've collected? Well, it's not so easy now because the hand is moving. So if I look at the immediately previous data point, the hand was in a nearby location, but it wasn't in the same location. Okay? So that sensor measurement itself is noisy, but also the hand has moved. Okay, so what are we going to do? So we could take the last 10 measurements and average them. Okay, so that's good because we're averaging out sensor noise, but the hand has moved quite a way over the last 10 measurements. And also, why take 10? Why not take 5 or 20? Who knows? Maybe a better thing to do, So if you think about this for a while, you think, well, the measurements I was making 10 minutes ago when the person was waving over here, they're irrelevant, all right? Measurements made a long time in the past are pretty useless. The current measurement, that's very valuable. It's noisy, but that's very valuable. The measurement I made just a little while ago is pretty useful because the hand was very close, but it's not quite as useful as the one I've just made, and it's more useful than the one I made 10 time steps ago. So somehow you want to pay a lot of attention to the current measurement, quite a bit of attention to the immediate previous one, and then less and less going back in time until eventually you've sort of forgotten what was happening 5 minutes ago. So that's maybe a sort of an intuition about how we should tackle this. The trouble with intuitions like that, of course, is they may be a good thing to do or not a good thing to do. It's hard to tell. And there are lots of parameters. How far back in time should I go? What weighting function should I use? And so on. So instead of doing that, I can just build a probabilistic model that describes this process of a hand moving in these noisy measurements. I'm just going to build a generative model that describes this situation. Okay, and when I do that, I'm going to make explicit all the assumptions that I'm making about the world. So that's the first stage, build a model. Then I collect my data. I run inference, and I'll make predictions under that model. And if my intuition's correct, that model should just do the right thing. Okay? So if my intuition is correct, that I should give a lot of weight to recent measurements and less weight to earlier measurements, that's what the model will do. And if that was bad intuition, the model will do the right thing instead. And if the model doesn't work very well, maybe it wasn't a very good model, maybe I made some assumptions that weren't very good, that's fine too, because I've been very explicit about my assumptions. So I can go back and test my assumptions, and I can refine them and change the model. Okay, so let's see how we'll sort of express that idea of tracking this moving hand with a noisy sensor using a probabilistic model. So let's start with, so we have discrete time steps. You know, maybe this is a video, we're doing this 30 times a second. So imagine we're making these measurements at discrete equal intervals of time. And this is we start off at time 1, and we've just made a noisy measurement for the position of the hand. So this is exactly the same as we had already. So at time 1, the hand has some position, mu. We don't know what it is. So we'll describe that by a Gaussian distribution. And then we make a measurement of the hand. And the measurement, the sensor is noisy. So the sensor, effectively, in this generative view, it takes mu, it adds some Gaussian noise, some zero mean Gaussian noise, and returns that measurement, x, as its measurement of the position of the hand. Okay? So given only that data, I could run inference, and I'd get a posterior distribution over mu, and that's exactly as we had before. Now let's move on to the next time step. Now the problem is the hand is now going to move a little. What that means is I have to introduce another variable. The variable I have to introduce is the position of the hand at the next time step, because it's different from the position at time step 1. So time step 2, the hand will have moved. It has a new position, mu2, if you like. And so that will again be represented by a variable in our graph. And again, we'll treat this as a Gaussian. And its mean will depend upon where the hand was before. So imagine I'm moving my hand like this. I'm tracking it at 30 frames a second. So at each frame, the hand is moving a little bit from one frame to the next. So the position of the hand at time 1 is a pretty good clue as to where it's going to be at time 2. Right? It's going to be near, won't have moved very far. That's what we're assuming in this model. So I'll take the position at this time, mu, to be a Gaussian distribution whose mean is equal to the value of mu. Okay? So if I knew where it was at time 1, then my model for it is at time 2 is sort of a Gaussian blur of that. Okay? Now, just pause the discussion and make a little aside. So if those of you who know about Kalman filters, if I'm really doing a Kalman filter like this, I'll make a slight refinement. I won't just track the position. I'll keep track of the position and the velocity. Because if I know where it is and I know where it's moving, I can predict where it's going to be at the next time step. So the position at the next time step is the old position plus velocity and times delta t. Okay? So if you're doing this for real, use a slightly more complicated model where this state is the position and the velocity. And I'll keep track of both of those. Okay? That's a little aside. Back to the tutorial where we'll just keep track of the position. Okay? So in this simple model then, this is a Gaussian whose mean is given by mu, and but it has some blur on it. It has some noise as well. It's different from this noise. This noise is as a model of the sensor. Okay? This noise is here because my model isn't perfect. Okay? This model is not an exact model. The reality is, the hand is accelerating and it's doing complicated things, and I can't predict exactly where it's going to be. So I have a very simple model, which is this linear model, and I add Gaussian noise to sort of account for the fact that the model isn't quite right. So my model of the difference between the hand where the hand really is and my simple linear prediction of where it is, that difference is I'm going to call noise. Okay? So there are now two variances or two noises. There's the noise on the sensor and there's this sort of Gaussian blur as we go from one time step to the next. Okay, so at time step 2, the hand is on some new position, and again I make a measurement, and that measurement, just as before, is a noisy version of mu. So I add some Gaussian noise, and that's my observation at time step 2. Then I carry on. Time step 3, the hand has moved a little bit, so I model that movement, and then I make another measurement, and I model that noisy measurement, and so on. Okay. Yeah. Okay, the question was the process noise, or process noise, as we say in England, changes. Okay. In this model, I'm assuming that the noise process on the sensor is fixed. The sensor has some particular property. It always adds Gaussian noise, and that Gaussian noise has a particular variance. That variance is constant. I'm also assuming that the Gaussian blur from one step to the next is shared. So it's the same Gaussian blur from one step to the next. Now, you know, the lovely thing about these, this is the whole point of these lectures really, is when somebody says, oh, but hang on a minute, I've got this tracking problem. In my tracking problem, the variance keeps changing. Fantastic, you model it. Okay? If you say my variance sometimes is this and sometimes it's that, it switches backwards and forwards. Fantastic, we can model that, and I'll show you a model of that in a minute, a bit later. Yeah. So this is my model. And I'm making it very simple because it's a tutorial. So in a real Kalman filter, at the very least, you'd probably do position and velocity, and then maybe you've got some weird thing. You know, you've got a radar measurement of the position and a video measurement of the position. That's great. You can model both measurements. You just build the model. Okay, it really is a delightful way to do machine learning. Okay. I'm not biased in any way. This is gospel. This is true. Okay. Now this thing is called the Kalman filter, and at least, you know, from my point of view, it seems very clear what we're doing, very clear what the assumptions are. And what about the equations? We now need to sort of code this up and compute mathematically what these distributions are. You already know how to do that. We derived that yesterday. This is actually a tree-structured graph. And you know how to do exact inference in time which is linear in the length of the graph by message passing, by computing those little messages. We derived exactly how to do it yesterday. All you need to do is to plug in the formula for the Gaussian distribution and just work out analytically how to do those summations have now become integrations, but they're all fairly easy. Okay, so I think that's just, you know, by far the cleanest and simplest way of deriving the Kalman filter, of understanding what it is and deriving the equations. Oh, by the way, it's also exactly the same as the thing called the hidden Markov model. The hidden Markov model is at the heart of all speech recognition systems. Okay, all modern speech recognition systems use a hidden Markov model to deal with the sort of nonlinear warping of the time axis. You know, if I'm speaking, I might speed up at the beginning of the word and slow down at the end of the word. It's the same word. I need to take account of that time warp using a thing called a hidden Markov model. It's exactly the same model, but instead of having Gaussian states here, you have discrete states. And again, there's an exact inference algorithm involving message passing along this graph. It's called the forward-backward algorithm, right? But it's exactly the same. It's just a particular case of the sum product algorithm we derived yesterday. Okay, so you sort of get that for free as well. And of course, historically, the Kalman filter was derived by one community of people interested in sort of missile tracking and radar and things. And hidden Markov models were developed, say, in large part in the speech community, and they derived all these equations, and it's only later that we've realized they're just special cases of the sum product algorithm on these graphs. Okay, so let's just go through that again and just watch the inferential process. So imagine we've built this model, we're now going to use it for real. So let's actually run the model in real time. So we're going to do real-time tracking. So we start off, we've not yet made any observations. We start off with our initial prior distribution of where the hand is. We don't know where it is. It's somewhere in the field of view. This circle represents a contour. We're now going to go from 1D to 2D. So this is a contour of constant density over 2D position space. So you imagine this as a Gaussian. The mean is here, and it's sort of bell-shaped and it's spread out, but it's very broad. We don't know where the hand is because we haven't made any observations yet. Now we'll make a measurement. So there's the hand. We're going to measure the position of the hand. So we make a noisy measurement of the hand position. So that's our observation. So this node is shaded in because it's now an observed node. It's not a random variable, it's an observed node. We know the position of we know the value of the sensor measurement at time 1. So now we can run inference. Now we run our little message passing algorithm, which in this case is just equivalent to a simple application of Bayes' theorem, and we get a posterior distribution over this Gaussian node. So what does that look like? Well, it's a sort of blend between the prior distribution and the information coming from this noisy measurement. So let's say it looks something like that. Okay, so that was the prior. Now we incorporate this measurement, and it does that. So it's shifted towards the data point. It's much closer to this measurement, and it's narrower because we're less uncertain about where the hand is. We've learned something about the position of the hand from the measurement. The mean of this isn't quite centered on the mean of the measurement because it's sort of it's still partly influenced by the prior. It's determined by the prior and the likelihood function from this noisy measurement. And it doesn't have zero variance because we've only seen one data point. So that's our current distribution over the position of the hand. It has some uncertainty. Now we're going to propagate forward one time step. So effectively what we're doing is we're making a prediction for where the hand is going to be at the next time step. Okay? And so in a real Kalman filter would track position and velocity as well, probably. So we've got some prediction for where the hand is going to be at the next time step. So this is our distribution, our posterior distribution here, and we propagate that forwards in time. The mean shifts. Right, it looks like the hand is moving to the right, so the mean of this is shifted to the right, but it's got bigger again. Okay, the variance is increased. And that's because of the variance associated with this Gaussian conditional distribution. It's adding this Gaussian blur. The uncertainty is increasing again. Okay? You know, there's the hand. I make my noise measurement, and I close my eyes, and I predict where it is, but I become more uncertain because the hand's moved somewhere. Okay? But not a problem, because I can make another measurement. So there's my measurement at time step 2. I now incorporate this measurement. So I'm propagating messages. I only have to propagate messages forwards in time around this graph. So I propagate messages up here. So I combine this message with this message, and I get a posterior distribution here. And again, it shifts towards the noisy measurement, and its variance decreases. Same again. So this is my current posterior distribution at time step 2. I make a prediction of where the hand's going to be at time step 3. The mean shifts. The variance increases again. I make my noisy measurement. I run inference again, and the variance decreases. Okay. So that's the Kalman filter. And that's all it is. In some applications, if I get time, I'll show you a quick example. Usually we're doing this in real time. All we care about is where is the hand now. We don't care about historical data. Sometimes, though, we're interested in, so we're going to say, well, where was the hand back at time 0? Okay, now if you think about it, if I've been measuring later positions of the hand, they help inform what's going on earlier. So again, you have this sort of intuition. If I know where the hand is going to be a 30th of a second from now, that gives me useful information about where the hand is now. In other words, I can send information backwards in time. And we did that yesterday. We had this notion of sending information one way on the graph and then the other way on the graph. So there's a message going in each direction across every link. And that allowed me to get posterior marginals for every node in the graph. I could do the same thing here. I could propagate messages also backwards on the graph, and I could get a new distribution here, a posterior distribution, which takes account not only of this data, but also all the future data. Okay? That would be another 3 chapters in one of these Kalman Filter books, but it's just the same rule that we derived yesterday. It's absolutely no different. That's called the Kalman smoother. All right? In hidden Markov models, you would use this because, not in real time necessarily, but particularly when you're training, you would propagate information back in time, so you could do a good time alignment for learning these models. And that's called the backward algorithm. So the forward pass in the hidden Markov model is called the forward algorithm, and then the backward pass through time is called the backward algorithm, so it's the forward-backward algorithm. In Kalman filters, it's called the Kalman filter algorithm, the Kalman filter equations, and the Kalman smoother equations. Okay, they're all there's just the sum product algorithm. Okay, everybody happy? Any questions? Okay, we had a question about the noise level. What about this noise level? So far, I've just said, there's some noise on the sensor. Okay, and there's some Gaussian blur. What is it? How am I going to choose that? You know, maybe I know a lot about the physics of the sensor, and I know what the noise level is. That's great. Perhaps I don't know anything much at all about the noise level. I have a rough idea of what it is, but I don't know precisely. Well, that's fine. I can now model it. Okay, it's an unknown quantity. I'm uncertain about it. So I describe it by a probability distribution, and I run inference. It's great. Okay. So let's do that. And again, just to keep things nice and simple, let's go back to the case where the hand is stationary. Okay, just to be really simple about this. The hand is stationary again. I'm going to get multiple measurements of a stationary hand using a noisy sensor. So my measurement, my distribution, so X is the thing that I measure. It has a Gaussian distribution with some mu, and my goal ultimately is to find mu. But it has a variance governed by a precision parameter, lambda, the reciprocal of the variance, and that precision, we'll imagine, is also unknown. So I want to know this value for mu. I don't know mu, so I have a Gaussian distribution over mu, the position of the hand, but I also don't know the variance. So I'll put a probability distribution over the variance, and so again so the variance becomes a random variable described by a node in the graph, and it has some distribution. And so the prediction model for X is a Gaussian whose mean is given by the value of mu and whose precision is given by the value of lambda. Okay? And now I can learn mu and lambda. Now, X was a measurement on the real axis, and we chose that distribution to be Gaussian. Its mean also lives on the real axis. We chose that to be Gaussian. Gaussian wouldn't be a good choice for the distribution of lambda, because lambda is the precision. Remember, it's the square of the variance. The precision is a non-negative quantity. So if I modelled it by Gaussian, the Gaussian can go positive and negative, and so I'd end up with negative precisions, and life would all go horribly wrong. So I need a different kind of distribution. So what I'm starting to do here, I'm going to use my third kind of distribution, because yesterday we had discrete distributions, now we've got Gaussian distributions, and now I'm going to introduce a distribution for lambda. These are like building blocks. So these little factors are like building blocks, and I'm going to add a third building block to my sort of playpen. And using these building blocks, we can construct all sorts of different models. And of course, there are many, many other distributions that we can use to bolt together. So we need a distribution for this non-negative precision, and the thing we're going to use is called a gamma distribution. That's its expression. That's a plot of the gamma distribution. So it's a distribution over lambda which goes from 0 up to plus infinity. It has a couple of parameters, and according to the choice of parameters, I can get different shapes of distribution. And this is an example of what's called a conjugate prior, a slightly technical point, but it just means that it has, it's a distribution of a lambda that's very well matched to the distribution whose parameters it's describing, in this case the Gaussian. So it just has nice mathematical and computational properties. So if you're not familiar with conjugate priors, there's a very good textbook which describes these in great detail. Okay, so definitely worth understanding the basic ideas of conjugate priors. I won't dwell on that now, though. Okay, yes, let's look at this situation again, a little bit more detail. So we've got this. We want to know where the hand is. The hand is stationary. We're making multiple noisy measurements. And now suppose we want to make a prediction. Supposing, for some reason, we want to predict the next sensor measurement. Okay, I want to predict what the center is going to show me on the next time step before I've measured it. Okay, because in machine learning, very often we want to make predictions. We want to predict the stock market, or we want to predict, all sorts of things. So it's all about predictions. So we want to predict the next sensor measurement before we observe it. So we've got our model, our Gaussian noise process, and we can use this model then to predict the next sensor measurement. The next sensor measurement is going to have noise on it, okay, because it's a noisy sensor. But also, if we've only seen a limited amount of data, we're not sure where the hand is. Okay, so there are two kinds of uncertainty in our prediction. We're uncertain about the next sensor measurement because, first of all, we don't know exactly where the hand is, but also the sensor measurement itself is noisy. So these two kinds of uncertainty add on to each other. Okay. So we've made some number of measurements of the hand, of the sensor, from the sensor already, of X. We can run inference, and we can get posterior distributions over both the position of the hand and the precision of the noise process in the sensor. And given those, we can then predict the next sensor measurement. So the next sensor measurement is another variable, so it gets a node. It's unobserved, so it's an unshaded node. Its distribution is just this same Gaussian distribution. It shares the same noise process because we're assuming that the noise process is fixed, okay, in this model. And the hand position is fixed, so its mean again is given by mu. So think about what happens as we increase the number of data points. As we get more and more data points, these distributions over the precision and the mean mu become narrower and narrower. I see more and more measurements of this hand position. Okay, the average of those points is a better and better measure of the true position of the hand. Or to put it another way, the posterior distribution of a mu is a Gaussian that's becoming narrower and narrower. And the limit of n goes to infinity, it becomes a delta function. And it's just, at that point, the prior has become irrelevant. Right? It's a delta function. It's centered on the average of the large number of measurements I've made. Likewise, after I've seen millions of data points, lambda has become a distribution that's also become extremely narrow. And it's centered on just the empirical, or the precision, the reciprocal of the empirical variance of the measured data points. So it's just your intuition. If I've got this noisy sensor, but I make millions of measurements, okay, then the hand location is just the average of those, and the noise on the sensor is just the variance of those data points. When I make my prediction, I'm still quite uncertain about the prediction, because it's still a noisy sensor. So this next sensor measurement will still have the full amount of noise uncertainty, but there won't be any uncertainty about the value of that noise, and there won't be any uncertainty about the position of the hand. Okay? But for finite data points, this posterior Gaussian distribution has three contributions to its variance. There's the noise on the sensor about which I can do nothing. That's there forevermore. There's the uncertainty in where the hand is, represented by the variance of mu. And there's the uncertainty in the value of the noise, represented by the variance of this distribution. So three sources of uncertainty. In the limit of infinite amounts of data, these two sources of uncertainty go away, but I'm always left with the sensor noise. So it might help to think about, remember that bent coin. So forget the heads and tails, just think this is a bent disc. When I flip the disc, it might have a higher probability of landing concave side up than concave side down, or maybe the other way around. I don't really know. I've never actually tried it, so I don't know. But I could make measurements. I could flip this disc lots of times and see each time I'd measure either concave side up or concave side down. Okay. After I've made millions of measurements, I would know with great precision the probability of it landing concave side up. Perhaps I've discovered that to very good precision, it's going to land 60% of the time concave side up and 40% of the time concave side down. So I know that probability with great precision now. But for the next flip, I don't know that it's going to be concave side up or concave side down, but I do know the probability of it being concave side up with great confidence. Okay, if you appreciate the difference. Okay. I've laboured the point, but I've actually laboured it for a reason, which has to do with this phrase big data. So you can't have not heard of the phrase big data. So it's this I think is actually there's a lot of hype around big data, but I think it's very fundamental and very exciting for a simple reason. But Bernard yesterday gave a lovely sort of history of machine learning. And he talked about all the great ideas that all these clever machine learning people have had over the years. And then somewhere in there, I don't know if you noticed, he threw in a little remark. He said, well, of course, actually, Moore's law helped. You know, faster computers have helped a lot. And really, the entire computing revolution has been built on one simple single fact, which is that the number of transistors on a piece of silicon doubles every couple of years. That's Moore's law. Okay? And the reason Moore's law is so fundamental is because it's exponential. Okay, now you all understand exponential growth, but even I have to remind myself constantly how extraordinary exponential growth is. It's so utterly different from the sort of linear or sort of polynomial growth that we see in everyday life. It's fundamentally and utterly different from anything we see in other technologies and other spheres of life. And everything has been built on that exponential growth. What we're seeing now is, for the second time in human history, another kind of very fundamental exponential growth in technology. It was exponential growth in the amount of data that we have in the world. So this, again, seems to be doubling about every couple of years or so. So the reason I'm excited about this is not for the usual reasons around the hype of all the things we can do with this, but just the fact that it's another exponential growth, and it looks set to continue for many, many factors of 2. And so we have the exponential growth in processing power. We now have exponential growth in the amount of data that we're collecting and storing. You know, that's got to be big news, okay, in all sorts of ways. It may not always be good news, but it's going to be big news, okay. And if you're in the field of machine learning, well, you know, the data itself is worthless. What you're interested in is the information that you can extract from the data, and that's the job of machine learning. So I think, you know, you guys are in the right field at the right time. But I want to just make a comment about the word big. So big data generally means data that you've got so much of it that you have to worry about storing it, you have to worry about moving it, you have to worry about computing with it. But I want to emphasize that there are 2 notions of the size of a data set. So I'm going to illustrate that with 2 sort of extreme examples. So let's consider, I'm doing some electrical measurements on a system, and I'm measuring the current for different voltage settings, and I get a bunch of points like this. And my goal is to predict the current for some new voltage. Now, my local friendly physicist has been really helpful, and she has told me that the relationship is linear, it's a straight line. So I can fit my straight line using my whatever, least squares algorithm, whatever you want, and now I can make predictions. Now, 2 points, of course, define a straight line, but these measurements have a little bit of noise on them. But nevertheless, a few noisy measurements pin down a straight line very well. I could build a probabilistic model of this, okay, and I get a posterior distribution over straight lines, but it would be a very tight distribution if the noise is small, because 2 points define a straight line. So a few noisy points define it with great precision. So 7 pairs of numbers, right, 7 voltages, 7 currents, 7 pairs of numbers allow me to make very good predictions of the current for this new voltage level. And if I gave you another 1,000,000 data points, it would help, but it wouldn't help much because you're already making really good predictions. So the next terabyte of data isn't going to do you much good. So that's an example of a data set that is computationally tiny at 7 pairs of floating point numbers, but statistically it's already quite a large data set. The other extreme is, here's an example at the other extreme. Imagine I've got these images. Each image contains millions of pixels, so it's computationally each image is taking up a decent amount of storage. Maybe I've got millions of these images. So this image data set is computationally a large data set. Let's suppose that I'm going to recognize objects in the image, and for the moment, let's just be naive and pretend we don't know anything about computer vision. We're just going to be naive machine learning people. We're going to treat these as vectors. We're going to feed them into our favorite classifier. Not a good way to recognize objects. But let's think about this. Each of these objects, let's say the aeroplane, when we think about all the images that are labeled aeroplane, well, there are many different kinds of aeroplane, different numbers of engines and different manufacturers and so on. They come in different colors. They can be viewed from different distances. They have different sizes. They can be different positions in the image, different orientations. They can be occluded. There can be things occluding them. They can be lit in different ways. There are shadows, reflections, and all sorts of things. All of those things are still aeroplanes, and all of those different variabilities can occur in combination with each other. So every choice of position, I can choose a different color, I can choose different lighting, and every combination of those is exponential in the number of things that I have to vary. So 1,000,000 images of an aeroplane is still very sparse in the space of possible images of aeroplanes. So at least if I don't do sophisticated and clever computer vision things, that is a data set which is computationally large but statistically small. So if anybody says, well, hang on a minute, we're in the world of big data, we've got terabytes of data pouring in, all of this stuff about uncertainty, we don't need any of that because you've already seen that as you see more and more data, the uncertainty becomes less and less and eventually becomes certain. Okay? Nothing can be further from the truth. Okay? Uncertainty is more important than ever in the world of big data. We have data, we have to deal with data that is computationally large but very often statistically small, and handling uncertainty is crucial. I'm going to show you an example, I think, next, where you'll see the power of modeling uncertainty. So that's just a little thought about the word big data. Finally, that's, sorry, I've changed the color and the notation, but I just had these pictures to hand. That's the Kalman filter, or the hidden Markov model. Somebody said, oh, what if the noise process changes? What if this is different? What if my application is different from yours? That's great, you model it. Okay, so let's suppose that your measurements depend not only on the hidden state, but also on previous observations. You just model that. Effectively, you're adding links to the graph. You might have sort of inputs as well as outputs. Again, you just model those variables and put the appropriate links in, define the appropriate factors, and so on. You might have multiple states. So a nice example of this is the so-called switching state space model. So imagine that there are different, let's say sometimes I'm sort of waving like this, and sometimes my hand is doing this, and then it switches back to doing that again. Well, I could capture all of those different things in one gigantic hidden state space. It gets very complicated and messy. And also, it doesn't capture the fact that sometimes the hand's doing this and sometimes it's doing this. So instead, what I can have is effectively one Kalman filter that models this sort of behavior. In other words, one chain of continuous Gaussian units modeling this, another chain of continuous Gaussian units that's very good at modeling this, and then another chain, a third chain not shown, of discrete units, like a hidden Markov model, which is the switch. And the state of that discrete variable says either I'm doing this or I'm doing this. So the generative model is at each time step, I first of all decide if I'm doing this or I'm doing this. If I'm doing this, I now draw a noisy measurement from the Kalman filter that's doing this sort of motion. Okay? So again, I just sort of describe my world. My world is that sometimes I'm doing this and sometimes I'm doing this, and I just model it probabilistically. Okay, it sounds great, doesn't it? There's a little catch that you might have spotted. It was very easy for me to say, oh, we just add another chain, draw in some nodes, that's our model. Some poor person has to go and code it up. Oh boy, you've got to sit down, work out all those forward-backward equations. Very easy to derive, we saw that. You've got to write them all down. Then you've got to code them all up. Well, you make errors deriving, you might make errors coding them up. No, it's all a big headache. Wouldn't it be great if the process of running the model was as simple as the process of designing it? If I could stand here and say, oh, your problem, you've got this strange problem, it's different from other, anything we've seen before. We need some extra hidden units and some extra whatevers. We'll draw the graph and we can construct the model in 10 minutes or so, but now we need to run that model. Wouldn't it be nice if we could code it up in another 10 minutes and run it and do good inference on it? Okay, so that's the sort of second part of this final talk. Before we do that, I'm just going to show you briefly another case study. And before we do that, we have a question. Yeah.
So if I take the 30 frames per second camera, but instead just up the frame rate by like factors of magnitude, it seems like I'm getting far more observations, but is it indeed true that I'm actually going to also reduce the variance throughout this model?
Okay, the question then was, what happens if I can up the frame rate, instead of 30 frames a second, measure 300 frames a second? It's always good to make more measurements. So if you've got a better camera that has lower noise variance on the sensor, that's always better than, that's better than you can do with the original data. If you can get higher frame rates, that's going to give you more information. So better data, cleaner data, more data, those are generally always good things to have. But the fundamental process of modeling that won't change. You'll be modeling 300 frames a second instead of 30. Yeah. Any other questions? How do you think you'd handle two hands? Okay, so if I've got what is my generative model? I've got two hands. So there's a position of the left hand, there's a position of the right hand. Now what are they doing? They're moving. So I've got Kalman filters. Oh dear, one hand can go in front of the other. Oops. I better have another variable saying which hand is in front, and I better have an emission model for what happens when one hand occludes the other, and what do the sensors see? Okay, you build the model. Question. I can't quote the literature offhand. The question was, what was I talking about? What was the name of the model? So generally they're called switching state space models, because these things are called, those hidden chains are called state spaces, and the idea of a switching model, you have multiple state spaces, and then you have some discrete state space that switches between them. And quite a few people have worked on it. Zubin has worked on inference in those models. He's speaking this afternoon. You can ask him about inference in his inference talk. He'll probably mention it anyway at some point. Yep. Any other quick questions? Okay, let's briefly look at a case study. So we should be able to go through this fairly quickly, because you've sort of seen all the ideas so far. So this is a real-world example now, not a toy problem. It's called True Skill. It's the problem of modeling user skill on Xbox Live. So this is the Xbox Games console. This is Xbox 360. It was launched in 2005, along with an online service so people can play computer games online against other people around the world. And these numbers are out of date. I mean, it's been growing rapidly, but it's an application at scale. So this is the system I'm going to be describing. It's been running 24 hours a day, 7 days a week, processing millions and millions of game outcomes. And it's important because we need to know the skills of players. First of all, to have a sort of leaderboard to see who's best, who's the second best, and so on, because people are competitive and they want to get up to the top of the leaderboard. But also because we need to do real-time matchmaking. So in the online server, you say, I want to play a game of whatever, and then with the next few seconds, it will match you up with people around the world who have similar skill levels so that you have a good gaming experience. So it's good to be able to have quick but accurate estimates of people's skill levels so you can match them quickly against people of similar skill level. This is work done by colleagues of mine. Ralph Harebrick is actually one of the lecturers at the summer school next week. He was at Microsoft Research for a number of years. He moved to Facebook. He was there for about a year, and he's now at Amazon. Tom Minker is I mentioned yesterday, he invented expectation propagation as his PhD, and that is currently the leading scalable inference algorithm in probabilistic models. And Tori Greppel is another colleague of mine at Microsoft Research in Cambridge. So what do people do before they had probabilistic modeling? What they did is a thing called ELO. So actually ELO was the system used on the Xbox before the Xbox 360 for inferring people's skill. So ELO is actually the name of the inventor. It's not an acronym. And it's still used today. It's the international standard for chess. So if you play chess, you'll have a chess rating, or chess rating is determined by the ELO system. And it just assigns a single number to every player. It's what we call a maximum likelihood system. In fact, you can derive it as a maximum likelihood limit of the true skill system that I'm going to describe. And it has various limitations. For example, it doesn't apply to more than 2 players. It doesn't apply to team games. Okay, so there's an example of what do I do if I have more than 2 players? What do I do if I have teams? In the modeling world, as you'll see, it's very easy. ELO, it just isn't applicable. There is another great advantage of moving beyond ELO, a huge advantage, which is to do with modeling uncertainty, and I'll show you that at the end. So let's tackle this problem of inferring people's skill using a model-based machine learning approach. So remember, there are 3 stages to model-based machine learning. We first of all build the model. The model is just a joint probability distribution of all the relevant variables. That might be expressed as a factor graph, for example. Then we collect our data, and we incorporate the data by clamping various nodes to their observed values. And then the third stage would be run inference. We use inference to compute posterior marginals of quantities in that model that are of interest. In a real-time application, we might iterate between 2 and 3. We might do some inference, and then we might collect some more data, like in that Kalman Filter example, then do some more inference, collect some more data. We might actually use our inferences to take action in the world. Otherwise, there's probably not much point in doing it. So we're interleaving inference and decision-making in these real-time applications, including in true skill. And if somebody comes along and said, hey, my situation is more complicated than that, we just extend the model. We'll see examples of that. Okay, so let's consider the simplest case. We consider 2 players. You and I are going to play a game of chess against each other. So one of us is player 1, and we have a skill level. We'll call the skill level S1 for player 1. And we're uncertain about the skill level, so we'll give it a probability distribution. And the simplest model we can have is a Gaussian. So now the skill of a player is no longer a single number, it's 2 numbers. It's a skill, it's the mean and the variance of their Gaussian distribution. Okay, so 2 numbers, a mean and a variance for every player. So there's our Gaussian distribution for player 1. Likewise for player 2, they have a Gaussian distribution. Their distribution might have a different mean and a different variance because perhaps player 2 is a stronger player. The mean of their skill is higher. Perhaps the variance is smaller because we've already seen a lot of data from them. We have less uncertainty. So those are our prior distributions for the skills of player 1 and player 2 in this particular game. So we're going to consider one particular game. And we'll have the notion of what we'll call performance on this particular game. So the challenge here is that, let's say I'm the stronger player, but nevertheless the weaker player will occasionally win. Now if I'm a much stronger player than you, I'll almost certainly win. If I'm a little bit stronger, I'll win slightly more often, but you'll win quite a bit. Okay? So we're trying to rank players, but it's a noisy ranking, because sometimes the weaker player will win against the stronger player. So what we'll do is we'll capture that by introducing some variance. So the performance of player 1 on this particular game is again a Gaussian variable whose mean is the skill, but with some added noise. Okay? And then likewise for player 2. And then the winner is simply the player who has the higher performance level on that particular game. Okay? So you can see that if this noise process is quite narrow, if there isn't much variability about your skill, a very strong player with a little bit of performance variability will nearly always beat a weaker player with a little bit of performance variability. But if their skill levels are very close in relation to the noise, if you like, on the performance distribution, then they'll be back to being almost 50-50 chance of who wins. Just a slightly increased chance of the stronger player winning. So that's a very simple model of two people playing a game of chess, or any other game for that matter. So then we observe who is the winner, and then we run our sum product algorithm that we derived yesterday. We pass messages around the graph, and then we can update the distributions. The means will shift a little bit, and the variances will narrow, likewise over here. And what we come out with then are posterior distributions after observing this new data point, this new game outcome for our two players. Okay? So our skills are still expressed by distributions. Question, yes?
I don't understand how come the performance of the player on that specific game does not depend on the other player.
The notion of this model is the following. I have a particular skill level. We don't know what it is, so it's modeled by a distribution. But I have a particular skill level. Now I'm going to play a game of chess. But in a game of chess, the stronger player doesn't always win, right? The weaker player can win. We've got to model that somehow. So I have the notion that when I play a game of chess, sometimes I play better on some days than other days. How well I actually play will vary from game to game. On average, the value of that performance variable will equal my skill, but there's a bit of uncertainty, there's a bit of noise in there. That's the model. You could think of more complex models. So it's probably about the simplest model that you could think of. And actually, it works really well. This is actually the model that's used in practice. Other questions? Okay, so I glossed over one little thing, was that the sum product algorithm we described yesterday doesn't quite work because we can't compute the messages exactly. And the reason for that, and the solution, is best seen graphically. So this is a picture or a plot of the skill of player 1 and the skill of player 2, and this is the probability, correct that. This graph is the performance of player 1 and the performance of player 2. And these dotted lines represent their skill. So let's say this axis is the performance of player 1. This is their skill value, the dotted line, and their performance is a Gaussian distribution centered on the skill. Likewise for player 2, this is their skill level, but their performance is a Gaussian distribution centered on their skill level. So in this joint space, it has this factorized joint Gaussian distribution. Okay. Now the winner is whoever has the higher skill level. So in this region, player 1 has the higher skill level, and in this region, player 2 has the higher skill level. So you could imagine in a generative model drawing samples. Let's fix the players' skills to known values, and now just draw samples for their performance values, replicating that game many, many times. Okay? Because of this Gaussian distribution is mostly in the red region, most of the data points will land in the red region, and player 2 will be the winner. And that's what we expect, because the skill of player 2 is bigger than the skill of player 1. But occasionally we'll draw a point in the blue region and player 1 will be the winner. Okay, the weaker player will win. And the more this Gaussian is shifted across, if I increase the skill of player 2, this Gaussian will shift more and more into the red region, and more of the sample points in our generative model will land in the red region, and a higher proportion of the time we'll have player 1 as the winner. If that makes sense. So this is our likelihood function. So let's suppose we observe that player 2, here this player, is actually the winner. What does that mean? It means that we rule out, remember in our generative, when we were doing the murder mystery, we observed that the murder weapon was the pistol. So we crossed off all the examples where we had poker or knife as the murder weapon. Okay, that was how that was sort of a quick and dirty way of doing inference. We can imagine the same thing here. So to do inference, we observe that the stronger player, the red player, is the winner, and so effectively we set to 0 all of the blue region. So this Gaussian distribution, this sort of 2D Gaussian distribution, now becomes a Gaussian distribution where somebody's taken a slice and everything to one side of the slice is 0. So it's sort of Gaussian on one side, and it has a cliff and it's 0. So it's no longer Gaussian. And this is a problem because if every time so that's the exact likelihood function, we can compute exact messages with that, but now we have non-Gaussian distributions. And if every time we take, because these players are going to go off and play against other players, and if every time we take funny slices through this multidimensional space, it becomes more and more non-Gaussian. And so what we do is we make an approximation. And this approximation is called expectation propagation. I'm sure you'll be hearing a lot about this in subsequent lectures and sort of deriving it more formally. But intuitively, all it corresponds to is taking this non-Gaussian distribution with this sort of cliff that's 0 in the blue region and approximating it by the best fitting Gaussian. And in fact, in this case, all it corresponds to is computing the mean and covariance, the mean and variances of this truncated Gaussian and using those as our approximate but Gaussian distribution. Okay, so we're taking this exact likelihood function and we're approximating the messages by projecting back onto the best fitting or the nearest Gaussian distribution. So we always remain within the family of Gaussian. So the true posterior distribution over skills is non-Gaussian, but we're going to approximate it by a Gaussian. Okay, and that's expectation propagation. This is a special case of what we call expectation propagation. So it's still the same process of sending messages, just as we described yesterday, but now we're approximating this particular message. Let's have a look at some results. So these are the results for 2 players out of a data set of thousands of players, and this is the number of games they play. Notice the axis here is 100, 200, 300, and we've got these two people playing this online game, not just against each other, but against lots of other people. And this is what ELO gives for their estimated skill value as a function of the number of games they play. And what you see is that everybody's starting off at 0, and as they play more and more games, their skill level is evolving, and you can imagine it sort of asymptoting, and eventually it will converge to some sort of skill level. If we take, and that's ELO, okay? ELO just has a single number for every person. Imagine that we now take exactly the same data and we analyze it with true skill. What do we get? We get a very different looking graph. What we see is much more rapid convergence in terms of the number of games played or in terms of the number of observations. So we can, so this is asymptoting much earlier. So instead of somebody having to play 100 or 200 games to get a good estimate of their skill value, they only have to play 2 or 3 or 4 games to get a good estimate of their skill value. So that's tremendously important commercially because people pay a monthly subscription to subscribe to the online service. And if they have to play hundreds and hundreds of games before they're finally matched against people of the right level and have a good experience, they're going to get quite fed up. So being able to estimate somebody's skill after a very few games is actually very important in practice. So the intuition of this is sort of roughly the following. Let's say we're going to play a game of chess. I'm the stronger player, and in ELO, my rating is 130. You're 120. Let's say you're the winner, okay? What happens in ELO is a little formula which increases your skill a little bit and decreases my skill. So I'd move down from 130, you'd move up from 120, and then we carry on and we play the next game. In true skill, imagine then that I'm 130, but I'm quite an experienced player. I've played a lot of games, and so my true skill distribution is quite narrow. So I'm 130 plus or minus 1. You are a newcomer, so you haven't played very many games. You're 120 plus or minus 20. So we've seen much less data from you, so the distribution over skills for you is much broader. Again, you're the winner. Now, I'm 130 plus or minus 1. You've just beaten me. You must be at least 129. I mean, that's the intuition. That's what's going on in this algorithm. So because we have the uncertainty in your skill value, and because of those particular uncertainties, the true skill algorithm will in one step increase your skill, roughly speaking, from 120 up to 129, because you've just beaten somebody who's much stronger for whose skill we're very sure. Okay, so because we have the uncertainties, the system will automatically, when appropriate, make very big changes to people's skill levels. Okay, it does the right thing automatically is the phrase I used. Okay, so a great example of where having a probabilistic, or if you like a Bayesian model, gives you dramatically better performance than if you simply don't model those uncertainties. Any questions on the true skill case study? I went through it fairly quickly because you've seen all the sort of machinery before. Yep.
Are you evaluating it on the chess players? I mean, it's interesting to track what your system says about them.
Great question. I have a slide on that later. Yes, there was a question about what happens for chess. I'll tell you later. Yeah.
Do you know how they assess if the method is actually accurate? I agree it's a good figure that it converges, but does it converge on the true value?
So the question was, does it converge on the true value? I mean, it's an interesting question because if you want to compare it with something, you need to measure that something else. You need to measure the true value. And this is our sort of model of how we measure the true value. You might ask if it's sort of calibrated. So for example, you might say, supposing we do the matchmaking using TrueSkill and we do the matchmaking using ELO, how often so if we're making good matches, then people should be equally likely to win or lose. Whereas if we're making bad matches, one person will just constantly winning, and so on. And it will take much longer for them to get good matches and balanced. And yes, the answer is it reflects exactly those graphs we've described. So if you use this to do matchmaking, people much more quickly get to the point where they're having balanced games. Yeah.
The graphical model you showed for TrueSkill has a structure, right? So once you observe two players playing against each other, the posterior of them is correlated.
Right.
Now with a very large data set, I guess you can't track that correlation, but,
Okay.
but you probably have clusters of people that play with each other a lot, right? So there could be sort of substructures that are very hard to capture.
Right, wow, lots of stuff there. Let me just repeat the question. So, smart question from one of the organisers, as you'd expect. Right, so it's been pointed out, and I sort of glossed over this, we have this V structure. Remember, that was a head-to-head node. When we talked about conditional independence, we said that these two things, they're independent. The skill of player 1 and the skill of player 2 are quite independent of each other. But now we observe that player 2 beat player 1. So player 2 beat player 1. If player 1 had a very high skill level, player 2 would have to have an even higher skill level. So these skills become correlated. That's our intuition, and that's what the graph says. So the true posterior distribution over these two players is correlated. Okay, and you can sort of see that from that likelihood. When we take that 45-degree slice, not only this becomes non-Gaussian, it no longer becomes factorized either. Remember, independence is factorized. And so really we're actually making two approximations here. The first approximation is that we're doing this EP approximation down here at this factor. We're saying, well, this true likelihood function would give rise to non-Gaussian messages, but we're going to project back onto the exponential family, we're going to project back onto the Gaussian family. So we're making approximations there. That's the EP approximation. The other approximation is that we're not computing the joint distribution over these two players. We are just computing their marginal distributions. So the EP is also making a factorized approximation. Okay, so two different approximations. We're sort of projecting non-Gaussian things back onto the Gaussian world, but also we're projecting from the correlated Gaussian world back onto the factorized Gaussian world. So those things are both going on in EP. And that's necessary for practical reasons. You've got millions of players. You can't work with the million by million correlation matrix of how their skills are all correlated. Okay, we just work with individual marginals. Let me slightly, I tell you what, since that's an inference question, I can punt that to Zubin, can't I? But let me just answer very briefly. The question was, are we increasing the uncertainty? Actually, the answer, it depends. So if I have imagine a Gaussian in two spaces, highly correlated, a long, thin ellipse, under an EP type of approximation, the marginals will be the correct marginals. So the marginals, right, will have the same variance as that distribution. They'll have the broad variance. But if you think of the products of those marginals, that's now a big circle. Variational message passing has a different behavior, and it will actually put in a small circle. It will capture the small variance. So it will capture something more like the conditional rather than the marginal variance. Okay, so it's making a different approximation. So in the first case, it's sort of increasing variances, and then in the other case, it's actually decreasing variances. And which approximation is appropriate will depend upon the model. And that's part of the challenge of doing accurate inference, which is why you have 3 whole lectures on it. So I'm going to stop there. Okay. Let me finish then with one final, but I think really interesting topic. So hopefully, I've convinced you that given some new application, you can build a nice probabilistic model, described, let's say, by a factor graph, very simply, that's bespoke and tuned to your particular application, that captures the key assumptions and the key properties of your problem, of your application. Okay. That's great, that's easy to do, but now you have to run inference. And at this point, you sort of sigh because you've drawn this big complicated factor graph, you're really excited about it, and now you've got to code it up, right? It's all really depressing. But no, there's a revolution in machine learning happening called probabilistic programming. So I think this is really one of the exciting frontiers of machine learning. And it's a nice intersection between the world of machine learning and a world that until recently was light years apart, the world of programming languages and programming language theory. And so in Microsoft Research Lab, we've always had programming language theorists right from the very first days of the lab, 16 years ago, and we've never spoken to each other, at least apart from socially, we haven't spoken to each other technically because we work in such different worlds. And now there's very close collaboration between people working in programming languages and people working in machine learning. So I think this is one of the really exciting frontiers of machine learning. And in the practical session with Tom Minker and Jordan Zakoff, you'll be using infer.net and you'll actually get to try this for yourselves. So let's imagine, so here's a conceptual language called CSoft. It's a representation language for probabilistic models. And the goal, and I'll use CSoft as an illustration, but it doesn't matter. The goal is quite fundamental, I think. I said that computation is undergoing a transformation from sort of handcrafted solutions to solutions that are learned from data. And it's undergoing a transformation from computation based on logic, because if you do computer science 101, it's all about determinism and logic. We're moving from logic to computation with uncertainty. And yet our programming languages don't reflect that. Our programming languages are all about the old world of computing with logic. And when we want to compute with uncertainty, you have to derive all the sum product algorithms, you have to code it all up and so on in that old style language. So the goal of probabilistic programming is to make uncertainty and random variables first-class citizens of the programming language, so you can program directly with uncertainty. And so CSoft is a conceptual language, it's more than a conceptual language, but it's an example of a language which incorporates computation with uncertainty. So it's based on a language called C#, and it adds support for three things. There are really three key words you need to add to a computer language in order to support programming with uncertainty. The idea of random variables, the idea of constraints, and the idea of inference. So we'll look at those in turn. But the point is that by building this into the language, we can intermix, as it were, sort of regular deterministic code and stochastic code. And that gives us a flexibility to do things that goes way beyond what we can do with graphical models, as I'll show you.
So just talking about stochastic code, does that mean that like actual generating random variables, or is it just working with probability distribution?
I won't repeat the question because I'm not quite sure. I think they're the same thing. So what we're going to do is introduce, well, I'm actually going to talk you through it now in great detail. So ask the question again in 5 minutes if you still have the question. Okay. So the first thing we need to do is introduce random variables. So normally in regular programming languages, any variable has a fixed value. It may be undefined, but if it has a defined value, it has a fixed specific value. So we might have an integer called length whose value is 6. But now we want to introduce random variables. Now we're going to work with probability distributions. So we might have an integer called length, but length is an uncertain quantity. So instead of having a value, it now has a probability distribution. And so we have a keyword, random, which says that length is a random variable, and in brackets we can specify its distribution. So it's uniformly distributed between 0 and 10. So the second idea is the idea of constraints. So we need to be able to introduce constraints on random variables. So here are some examples of constraints. You might have two random variables, visible and length, and we're constraining them to be equal to each other. Sorry, visible and... this is the fourth example. Two random variables, I and j, and we're constraining them to be equal. Okay? They're both still unknown. Neither of them has a precise value. They're both described by distributions, but we need to be able to say the distributions of these variables are equal to each other. We might constrain a random variable, let's say length, to be positive. So that's a bit like, truncating that distribution. We say any 0 or negative values for length are ruled out, but it's positive, and we're constraining the distribution in that way. But we're not fixing it to a specific value. Or we might fix it to a specific value. You might say length equals 4. So length might be one of these variables that we actually observe, and so incorporating data corresponds to taking random variables and constraining them to be equal to the observed values. The third thing we need to do is to run inference. So we have to have a third keyword, say infer, which says go and do inference. In other words, compute posterior distributions for me. So here's a simple example. We have an integer I, which is a random variable, and it's uniformly distributed between 1 and 10. So it's like a 10-sided die. I can take any value 1 to 10 with equal probability. We then compute a Boolean variable b. So b is true if I squared is greater than 50. Okay, so you think, so 7 sevens are 49, which is less than 50. So the numbers 1 to 7 will return false, and then 8, 9, and 10 will return true. So 3 out of the 10 numbers will return true, and 7 out of the 10 will return false. So I can now ask for a distribution, the distribution of b. It's called bdist, and I use the keyword infer. So I say infer. Okay? And somehow behind the scenes, the magic goes on and it computes that distribution. In this case, it's trivial. It's just a thing called the Bernoulli distribution. That's just the coin flip distribution, and its value is 0.3. Okay? Because 3 out of those 10 numbers will have I squared greater than 50, and the other 7 won't. Okay? So that's the inference. In general, of course, the inference is going to be a lot more complicated. So what this is doing, if you could imagine that we could build a language like this, it means that you can describe the probabilistic model very simply in this language, and then you call this word infer, and something extraordinary happens, because behind the scenes it's going to solve inference for you without you having to think and do anything. So that's the dream, okay? That's the aspiration of probabilistic programming. It's still, we've made a lot of progress, I think, in a short time, but it's very much a research frontier. How essentially the problem of automating inference is at the heart of this. So let's think about the relationship between graphical models that we spent a lot of time discussing and probabilistic programming. How would we build probabilistic models in a probabilistic programming language? Well, the basic thing that we start with are random variables. So if we have a Gaussian, so x is a Gaussian, and it has a distribution 0, 1, so it has a mean of 0 and a variance of 1, or a standard deviation of 1. And we represent that using the random keyword. So we define x to be a random variable, and its distribution is a Gaussian with 0 mean and unit precision or unit variance. So we have then a relationship between the thing we drew as the graphical model and a line of code in this probabilistic programming language. What about a more complicated Bayesian network? Well, here's a director graph. So here's a more complex graph. This is something that we saw earlier. This is a noisy measurement process, say the position of a hand. This is the unknown value of that hand position, and this is the precision of that noise process. So we have 3 variables. So we use the random keyword 3 times. So x is a Gaussian with 0 mean unit precision. Y is a gamma distribution with parameters 1 and 1. And then Z is a Gaussian distribution, but its mean is given by the value of x, and its precision is given by the value of y. So this graph corresponds to those lines of code. Okay, so quite easy to take the graph and translate it into code. What about plates? All right, now plates, remember the plate was just a convenient graphical notation for saying this piece of graph is replicated multiple times. Well, that just corresponds to a loop. So we define x and y are Gaussian and gamma distribution, and then we have a loop, and within the loop we have 10 random variables which are Gaussian with mean x and precision y. What about, let's do it the other way around now. Let's look at things that we might code up and see what they correspond to graphically. What about if we had an if statement? So b is a Boolean random variable, so it's a coin flip and it's 50-50 true or false. If it's true, we're going to execute this piece of code. We're going to define a random variable which is Gaussian with a 0 mean unit precision. If b is false, then instead we're going to have this, which is, we're going to define x to be a Gaussian with a mean of 10 and a precision of 1. Now, this is not like regular code. So regular code over deterministic variables, you test the value of b, and if b is true, you go and execute this piece of code, and if it's false, you go and execute that piece of code. b is now a random variable. So it has a probability of being true and a probability of being false, which means we sort of have to execute both pieces of code. Okay? So you can see it's very easy to write down, but what's going on behind the scenes is getting a whole lot more complicated, okay? Which is why this is, I think, a very interesting research frontier. What is the graphical notation for this? Well, it turns out it's very useful to have a piece of graphical notation. It's called Gates. It's developed by Tom Minker and John Winnett in Cambridge. And it's, if you think about this, what this is the graphical notation, this is the Boolean variable, and it either switches, if it's true, it switches on this piece of graph, otherwise it switches on that piece of graph. So according to the value of a variable, we're changing the structure of the graph, perhaps including a link or removing a link, or whatever. So now we have the structure of the graph which depends upon the variables. Remember we talked about conditional independence. A is independent to be conditioned on C, had to be true for every value of C. That's the standard conditional independence. This is a conditional independence in which the choice of links and the structure of the graph depends upon the value, in this case of this Boolean variable B. So this is a much more general notion of conditional independence. And this is very useful for doing efficient inference on mixtures, for doing model structure selection, for learning the structure of models, and so on. Lots of other things we can do in a programming language which simply don't have, nobody's bothered yet to write down a sort of a graphical equivalent, or it might be quite difficult to write down a graphical equivalent. So a probabilistic programming language is actually much more general, much more flexible than graphical models. It includes graphical models as a special case. How can we interpret a probabilistic program? So this is not how you would build one, because this would be wildly inefficient, but we can use our generative view, our sampling interpretation, to understand what a program means. So imagine stepping through the program. Every time you see the word random, you draw a sample from the corresponding distribution. Every time you see the word constrain, you test to see if the constraint's true, and if it isn't true, you stop and discard that sample. And if it's true, you carry on, keep the sample. And then when you reach infer, to infer some quantity x, you simply put x to one side in a sort of box. And you do this many, many, many times, and your box fills up with samples of x that are drawn from the distributions that satisfy the constraints, and so that distribution of x values that you've accumulated in your box is the result of your inference. It's your posterior distribution. So conceptually, that's what a probabilistic programming, what a probabilistic program means. You wouldn't actually implement it like that because it would be ridiculously inefficient. You'd use message passing and approximate inference and so on behind the scenes. So although this is a research frontier, there is there are probably about a dozen, I think, probabilistic programming languages around. Infer.net is one of them from our lab in Cambridge. And the focus of Infer.net is on industrial robustness and scaling. So other languages focus on different aspects. The focus of Infer.net is using fast approximate inference to do probabilistic programming at scale and in a way that's robust. And in fact, we use this already in several large-scale products. How it works in a nutshell is that you describe your model using a little snippet of code, and then you run through a compiler. This is the clever part, the compiler, which generates regular computer code, in this case in C#, which is efficient inference code for your particular model. So if you change your model, because you say, my noise process varies or something, so you expand the model a little bit, you recompile it, and you get new code that is efficient inference code for your particular model. That's just then fed through a standard compiler to produce machine code, which you then execute. Lots of standard models are already supported, so it's already really quite flexible. And I thought I'd finish, if I can just take one more minute, by just going back to that TrueSkill example and showing you how we can actually implement TrueSkill. Now, when TrueSkill was first implemented, it took a smart guy about 6 months to do this, a lot of hard work. And we can now do this in an afternoon. And I'll show you just the core code for how to implement TrueSkill in Infer.net. So remember, these were the variables. So this is the code. There are just some definitions there at the top. Then the skills are Gaussian distribution. So it says a Gaussian whose mean and precision is 0 and 1, similarly for the player 2. Then the performance of player 1 is again a Gaussian whose mean is the value of skill 1 and has some precision beta. And if you think beta is a magic number, you can put a distribution over beta and learn it from data, as we've discussed already. Then we have a constraint. So player 1 was the winner, so we must constrain these two random variables so that the performance of player 1 is greater than the performance of player 2. Then we want to do inference. So we create this thing called an inference engine, and then we ask the inference engine to tell us the posterior distribution for the skill of player 1 and the posterior distribution for the skill of player 2. By default, it runs EP, but you can tell it to run other inference algorithms if you wish. So finally, I said ELO was widely used in chess and other games, but it doesn't support multiple players, it doesn't support teams. But in the modeling world, in the model-based machine learning world, it's very easy to take our graph and just extend it, or a probabilistic program, and extend it to multiple players. So there's the graph for 3 players playing against each other. And these observations would say that player 2 beat player 1 and player 3 beat player 2. That's the same code as before. The stuff in yellow are the changes we need to make to the code in order to reflect the change to the model. Okay, no deriving messages or coding things up from, it's just as simple as that. What about teams? Well, here's a graph showing two teams, each of two players. They play against each other. And that's again, the original TrueSkill code, with in yellow the changes to incorporate players 3 and 4 in this team game. And in this case, we've assumed that the performance of team 1 is a Gaussian whose mean is the sum of the skills of the two players. We've assumed in this model that the skills are simply additive from the members of the team. And you could think of other models as well. And then finally, not only, coming back to the example of the hand, not only are we trying to work out a person's skill by observing multiple games, but their skill is actually changing. So like the hand moving, we're now tracking a moving target, because as you play lots of games of chess, you're probably going to get better at chess. It might get worse, but your skill can change through time. How do we model that? Well, this is the model that's actually used in practice. Very simple model. We just do the Kalman Filter thing. We had a little bit of Gaussian blur. So here are two people, they play a game, we update their skills, we get posterior distributions of skills. Those skills are now the priors for the next game, but for the next game, we allow the skill of player 1 to be a little Gaussian blur of their previous skill. That allows their skills to evolve in time. And again, a tiny change to the code to implement that. And then, very last view graph, which is to answer the question, whoever it was back there who asked me about chess. So again, colleagues of mine have taken historical chess data. You maybe can't read this. This is going from 1850 up to 2006. And 3.5 million game outcomes, 20 million variables, 200,000 players, 40 million factors in the factor graph. And I'll just fast forward. And this is how this is a subset of the players, various famous players, Paul Morphy and Kasparov and Karpov and Spassky. And this is how their TrueSkill means and variances have evolved through time. And here you see Bobby Fischer, pretty good chess player. And then at some point, the variance becomes extremely large. And the reason is he sort of went into hiding, became a recluse. We don't have any data for him. And so that Gaussian blur means his uncertainty, the uncertainty in his skill value is increasing. We haven't got any data from him. We don't know if he's getting better or worse in his hiding hole. And then very, very finally, just to convince you that this is interesting, this DARPA, the American funding agency, has just announced a $50-odd million program of research funding in probabilistic programming to try to encourage research in this area. And with that, thank you very much.